The first example we're going to look at is a function f15 is equal 15 divided by x squared minus 1. And what I'd like to do is, before sketching a graph of the function, I'd like to know the bounds, right? I don't want to get carried away. I'd like to know what are the vertical and horizontal asymptotes, or the values that just won't work. So first I'm going to consider the vertical asymptote, and at this point I want you to pause without looking back. I want you to sum up to yourself in a coherent sentence what I mean by a vertical asymptote, and then try and find it yourself, and then come back and check. Alright, so hopefully what we're thinking about for vertical asymptote are x values which will not work, right? We're looking for the restrictions on two sets of axes, right? We want to know x values that won't work, and we want to know y values that we'll never get, okay? And so in thinking about x values that we can't have, well, what would make an x value kind of not kosher, not cool, not acceptable? Well, if we're dividing something, then the problem would probably come by dividing by 0. So the question I'm going to ask myself for the vertical asymptotes are, what would make x squared minus 1 equal 0? And this is a simple quadratic, so I want you to think about what that means. Go ahead and consider it, and then come back. So maybe you went ahead and solved, and perhaps you got x equals 1, or the square root of 1. And if that's what you got, I want you to stop for a second, and I want you to think about how many roots will a quadratic equation of this form have. It could possibly have 1, but you'll also notice that a quadratic equation could also have 2 real roots, so you need to be careful. And if you were to solve this, what you would find is that in the intermediary steps, you're going to have x squared equals 1. You could also solve this with the quadratic formula. And, well, think about the values that you could square. What could you plug in for x, square, and receive 1 as your answer? Well, there's 2. There's positive and negative 1. And remember, that means when you square root both sides, I'm going to square root both sides, but I want to take the positive and negative version. So when I square root both sides, I'm going to end up with x is equal to plus or minus 1. And so in practice, that will mean I'll have 2 x values which will not be permitted, no matter where I am. I can never have an x value of plus or minus 1. Now let's think about the horizontal asymptote. Okay. And I want you to, again, stop, consider what we're thinking about when we say horizontal asymptote, and then go ahead and try and find it yourself. In thinking about a horizontal asymptote, we've already discovered the bounds on x values that won't work. Now we want to know what are the y values which we'll never touch or never approach. And so the way that we're going to do that is we're going to say, okay, as we're getting out further and further in the x direction, what is going to happen to our function? And so what we're wondering is, as x approaches infinity, what is my function going to be? And there are a couple ways that we can attack this. And I want us to start off by just thinking about this function in general. Okay? What is going to happen to the numerator as x gets closer and closer to infinity? Well, hopefully you said it's not going to change. 15 is going to be 15 no matter where I am on the x-axis. But now consider what will happen to x squared minus 1 as x approaches infinity. Well, you can imagine as x approaches infinity, x squared minus 1 is going to be humongous. It's going to be enormous. It's going to be just a gigantic number. And as you know, I'm sure have seen in practice, 15 is going to stay the same. So 15 divided by an increasingly large number, well, what's going to happen? Our function, I'll just define this as f of x. So as x approaches infinity, f of x is going to get closer and closer to 0. because 15 over infinity is 0. It's going to get really, really close to 0. And so we have another horizontal asymptote here. All right. I'm going to let that sit for a second, and when we're doing this next function, we're looking at the asymptotes of this next function, it will be ever more increasing the different methods we can kind of use to think about the horizontal asymptotes. So for our next function, we'll call this function g of x. Why don't you go ahead and try and find the vertical asymptote or asymptotes and the horizontal asymptotes. I'll put that up here. And then when you're satisfied, come check back. Alright, I'm going to create a small graph for us here. So I'm thinking about the vertical asymptote. We're again considering what x values can we not have. Okay, what will just not work? And in order for that to happen, well, it would have to have some sort of denominator that just doesn't work for us. So thinking about the denominator, what would make x plus 2 unacceptable value, or make it 0? And that's pretty easy. Clearly, it would be x equals negative 2. Now, I want you to stop for a second and remember that just because the denominator is 0 does not necessarily mean we have an issue, right? It could be that we have an issue. In all likelihood, we do. But what's the one scenario where the denominator of 0 does not actually present a problem? Well, you should be aware, right, that it won't present a problem so long as what is the case? Well, it won't present a problem so long as our denominator is not also 0, right? Because 0 over 0 is 0 itself. So quickly try plugging in negative 2 here. You're going to have 4 times 4, which is 8, plus 3 times negative 2. So we have 8 minus 6, which is 2, plus 7, which certainly is not 0, and so I certainly have a vertical asymptote at x equals negative 2. Okay. All right, now on to the horizontal asymptote. And so here we want to know what is going to happen as x approaches infinity. And well, it might be kind of tough for us to look at the numerator and denominator right now because there's a lot of x's all over the place, and certainly, we've got kind of a lot going on here. It's hard to tell whether certain pieces of our function are going to go to 0 or what exactly is going to happen. And so there are a couple methods that we can utilize to help us simplify our function into a formula and make it really easy for us to see what's happening. So the first thing that I would kind of recommend you think about is splitting this up into 3 pieces. So 4x squared over x plus 2 plus 3x over x plus 2 plus 7 over x plus 2. So why don't you go ahead and on your own write that out and just kind of think about what will happen to each piece of my function as x is getting closer and closer to infinity. Okay, good. Now, it may have dawned on you that what we're doing here is division. Okay, that's exactly what we're doing here. There's really no ifs, ands, or buts about it. And so, since we already know how to divide polynomials, it might make sense for us to simplify it by dividing, right? This is a division. And so we can actually divide the polynomial, and that will really help us simplify. And then, once we've done that, we can think about what happens as x approaches infinity. Okay? So, let's go ahead and do that. I have 4x squared plus 3x plus 7, and I'm dividing it by x plus 2. I want you to go ahead and do that on your own and check back when you're finished. So x will go into 4x squared, 4x 4x times 4x squared plus 8x. I subtract. I'm going to end up with negative 5x plus 7. This will go in negative 5 times. I will get a negative 5x minus 10. I'm going to subtract and end up with 17, or a remainder of 17. And now it's important to remember that the remainder, what do I do with the remainder, right? I add it and make sure that it's over the divisor, x plus 2. Because if this is something that you're confused with, go back and watch that video. But remember, what we're asking is what polynomial, that's our answer right here, what polynomial can we multiply by x plus 2 to get 4x squared plus 3x plus 7? And so when you multiply x plus 2 times everything here, well, you're going to get 4x minus 5 will give you everything but the remainder. And so you'll need to multiply x plus 2 times 17 over x plus 2 to get your remainder. So the function simplifies. We can rewrite our function g of x as simply 4x minus 5 plus 17 over x plus 2. And what's going to happen to this function as x approaches infinity? What is it going to get really, really close to? Well, I want you to stop right now. Think about what will happen to this function as we get really, really, really large values of x. What you should notice is that as I get bigger and bigger values of x, this piece right here, 17 over x plus 2, very similar to our original function f of x, this is going to get close to 0. Because I'm going to end up with 17 over a huge number, over infinity. And all I'm going to be left with is 4x minus 5. Now, in reality, right, the bigger values of x that I plug in, I'm never actually going to get 4x minus 5. I'm always going to be adding on some really small value. But I'm going to get really close to this. In fact, I can get as close to it as I want just by plugging in a really big x value. And so it's not a horizontal, it's a slant asymptote that I'm going to be getting really close to is 4x minus 5. So I really shouldn't say that g of x is equal to this. As x approaches infinity, g of x will approach 4x minus 5. And so in practice, what we can do to kind of sum that up for us is we can simplify our division. Right? All this is a fraction with polynomials. We can divide them to simplify it, and this simplified version makes it a lot easier for us to think about what happens as x approaches infinity. And so it will never ever actually reach this line. It's a linear line with a y-intercept at negative 5 and a slope of 4x. So it might look just like that. So those would be our asymptotes. Okay? I hope that was helpful.